here Patrick do it in a very complicated way. But essentially, in the end, is essentially what is observed for the y factor, the difference between the calculated y factor and the observed y factor. In the end, that's what it is. Okay. But what I wanted to show you is that here I'm plotting the Joner R factor. Let's talk about this. I calculate this error when I change one of the parameter in my model, right? So this is, I have one point. This is basically an error function that I plot, the residual function. And I change my physical parameter. So it could be the top layer spacing here. This is the spacing. And then this is a potential that I use, right? This is another modeling trick that the physicists use. So I can make a two-dimensional plot, and then basically I am minimizing, I'm trying to find the minimum point whereby I have the least residual that I got. And here it is. And this, once you find that, you can say, haha, this corresponds to the top interlayer spacing of minus 5% from this, right? From the expansion that I got of the origin space. Okay? So this is a way to optimize, if you like, because you are trying to find the minimum point of this R factor map. And that minimum point corresponding to a certain geometry. And that's how you determine, in a very roundabout way, of what is the most precise geometry model that give you this curve, that lead you to this curve. Because this curve is generally based on a model which rely on the parameter that you put in here. And then if you can calculate the least error, that must be the right curve. But this is one way to give you quantitative information about bond length and bond angle in your structure here. Okay, so that's just how people do this in LEED, and it's a very sophisticated, very elaborate, very complex calculations, and oftentimes it doesn't work all that well either when you have a very complicated system, because it's a multi-dimensional problem. Because in a unit cell like this, there are many atoms, and you know, there are many points in your calculation. And what's worse is that it really depends on the type of scaling theory that you use. Because depending on what type of scaling theory you use, you have different R factor map, and therefore you may have a different structure that you model here, that you optimize. Okay, so the upshot of all these discussions is that people were able to, using this type of technique, they were able to determine a field structure that's quite accurate. And this is listed here, right? So you can, there's some of the results of surface crystallography for clean sample, right? So these are clean sample. You can see they are all low Mueller indexes surfaces, like silver 111, gold 111, copper 111. They never were anything that's very complicated. They are mostly metal surfaces because electron scattering on simple system you can model quite easily. And what people have found using this IV curve measurement is relaxation, the bonding relaxation, which is another way of saying expansion or contraction, how far they contract or expand in the top layer versus the second layer, and so forth. And so there are some precision that you can get. I say up to date, there are less than 50 systems that's really well determined by LEED type calculation. So despite all this work, people still really don't know precisely where this atom is. So this is a demonstration of some of these patterns that you got. The little dotted line which you can't see on here correspond to atomic movement slightly from these positions to generate, from the LEED pattern IV curve measurement that you can determine from this. Okay, so next I'd like to tell you a little bit more. So much for electron diffraction, an important technique to look at surfaces, no doubt, but to look at object, neither object in particular, you need other tools. So So here is some common service science technique to look at services and therefore nilo object in particular. We just talked a lot about LEAD as a way to introduce service crystallography, and the couple of points that I like to talk about, which is XAP and STM, scanning tunneling microscopy. XAP is important for material science and therefore nanoparticle bulk type analysis, and STM, scanning tunneling microscopy, is very important to look at quantum wire, quantum dot type structure on a well-defined surfaces, conducting surfaces that you have. So I'd like to give you each of these. We have talked about, usually I classify them in three ways. We look at diffraction technique, which we have done on using the electron diffraction. And XAP is another diffraction technique, not quite using the electron. It is interference technique. It's kind of interference technique, not precisely using a primary electron beam, but it's an interference, as we'll see. And this is related to a technique called XPS, X-ray for electrons spectroscopy, that we'll discuss later when we are talking about electronic structure determination. That's why I like to tell you a little bit about this. XAP for a long time XAP was discovered, was popularized, if you like, in the early 70s, and then become explosive development in the mid-70s to 80s because of the invention of high energy physics facility called synchrotron. We'll talk a little bit about that. And really is a very powerful tool for analyzing bulk type material. You have nanoparticle, thin film, or absorbate. You can use it. It's a simple technique to look at, to use. A lot simpler, if you like, than LEAD. You don't necessarily require ultra vacuum. You can do this in air. You can nowadays you can do it in liquid. Very powerful in that sense, right? So it's a fine, what they call fine structure interference by technique. So I'd like to tell you a little bit about that because of relevance to material science. And then, just for you, or some of you know already that there's a course on XAP actually by Eric Bose, who done a lot of these LEAD measurement at various synchrotron in Europe that he's based on, that he makes these material science type measurement using XAP. And I think there's a course on XAP that you can talk about in great detail. I won't go too deeply into it. I just tell you an overview of what this fine structure technique is all about. And then something related to, quite exciting, I would say, related to interference is holography, this photoelectron holography. You know, the three-dimensional cinema that you see, right? This new movie that taking in $2 billion is based on holography. The 3D image that you see is an optical, is based on optics, and you can use the same thing to measure